So this is the research project for Group 12. We are exploring photoconductance decay lifetime characterization of defects in monocrystalline silicon solar cells. Today we'll be going over sort of a overview of our project, some of our definitions and objectives and the overall scope of what we would like to research, as well as a more detailed explanation of the artifacts of the data we are going to collect and how photoconductance decay can be used to characterize the solar cell samples we're working with, and then as well we will address some of the overhead tasks and progress we've made so far. So the project overview. The research project we're working on and the characterization of these solar cells can be broken down into two phases. The first is the measurement phase, where we'll take lifetime spectroscopy measurements using the Sinton Consulting WCT lifetime tester that Dr. Bernoulli has in her lab here at ASU. The second part of this research project will be actually taking this data and then applying an analysis to further characterize the samples that we're looking at, and that'll include being able to tell more information about like the surface passivation and surface recombination velocity of the charge carriers in these samples, as well as things such as the defect energy levels of the sample. Okay, diving into some of the more detailed theory, we can look at characterization using lifetime spectroscopy. So let's start with the introduction of carrier lifetimes. Lifetimes fall into two primary categories: recombination lifetimes and generation lifetimes. Generation refers to the process by which electron-hole pairs are created. The energy for the excitation of an electron from the valence to the conduction band can come from thermal processes or in a solar cell from the absorption of photons. By analogy, recombination refers to the inverse process whereby electron-hole pairs are lost due to spontaneous transition of an excited electron from the conduction band to an unoccupied state in the valence band. Since our goal is the characterization of defects in solar cells, we will be focusing on recombination lifetimes.
The most common classification of the different recombination mechanisms distinguish intrinsic and extrinsic mechanisms. The intrinsic are always present in the ideal crystal. They don't depend, for example, on the growth technique. They are inherent to the material, and in this sense, they are unavoidable. Radiative band-to-band recombination is the annihilation of an electron per hole involving the emission of a photon. The second intrinsic order is traditionally viewed as a three-particle interaction, where the energy released by the electron per hole recombination is transferred to a third carrier. Now, in the case of extrinsic, this decay does not occur directly via band-to-band transition, but by an electron transition via a defect center with an energy level in the band gap. This process is commonly known as Shockley-Rittenhall recombination. Shockley-Rittenhall formulated this theory of recombination in 1952 from statistical considerations, and this theory is the basis of the lifetime spectroscopy. Now, the main goal of this project, or the focus of this project, is the defect characterization in the bulk of crystalline silicon solar cells. So, here we have the different recombination mechanisms that happen within the bulk of the material. By using richer parametrization proposed for crystalline silicon, we will calculate the intrinsic contribution. And then, by using the very well-known established Shockley-Rittenhall theory, we can extract important parameters of the defect level, such as its energy and its capture cross-section. Now, what is lifetime? Why lifetime is important? So what we measure is the effective lifetime. So let's see the components of the effective lifetime. The four mechanisms that we discussed previously all simultaneously occur in the sample, and the overall lifetime, or the effective lifetime, is the sum of those individual recombination rates. The contribution from the bulk is represented by the summatory of the radiative, the Auger, and the Shockley read hull contribution. Then, if we add to the bulk the contribution from the surface, we obtain the effective lifetime. The main obstacle for bulk defect characterization is that often the shape of the contribution from the surface is superposed to the bulk, as we can see down here in this mathematical equation. Usually, because of that, the surface recombination is just considered constant or completely ignored. But in this work, we will going to explore the methods to separate the bulk lifetime from the effective lifetime. Now, another important feature of the lifetime curve is that the lifetime curve shows important fundamental parameters of the solar cells, which are evaluated when the material is under different injection conditions. So, to address the problem of the surface superposed to the bulk, we're going to explore the thickness variation technique. In order for this technique to be valid, we need a really high quality passivation, so we can approximate the contribution of the surface as 2 times the surface recombination velocity over the thickness of the sample. So, by measuring the effective lifetime on a set of samples with different wafer thicknesses, and plotting the data in a 1 over effective lifetime versus 1 over the thickness diagram, a straight line is obtained, whose slope is 2 times the surface recombination velocity. Then, after the surface contribution is obtained, we can subtract the surface from the effective lifetime, obtain the bulk, and by calculating the intrinsic contribution, we can extract the Shockley read hull contribution, and therefore we can extract the defect parameters. A second option is the use of a control sample. By doing so, we are assuming, or our main assumption to do so, is that the contaminated or the sample with defects and the control have the same intrinsic and surface contribution. The problem with this method is that a control sample is not always available, and also that sometimes the defect could interact with the surface, making our main assumption invalid.
So now we'll be talking about how we're going to obtain these recombination lifetime measurements using photoconductance decay, or PCD. PCD lifetime characterization technique was proposed in 1955 and has become one of the most common lifetime measurement techniques. It's widely used. For our injection range, 10 to the 13 to 10 to the 17 per centimeters cubed, and the temperature range is from 25 C to 230 C. See this test apparatus. Down here is our sample, the silicon test wafer reference cell. You flash light onto it, and then this coil basically helps to measure the amount of generated carriers. So from this equation down below, we can find the effective lifetime as a ratio of the generated carriers over the generation rate minus the change in generated carriers over time. As far as tasks for our project, we've broken it down into a couple different portions here. First task is going over and researching the theory that we'd be using in this project. After that, we would be doing the actual data acquisition using the Sitten Consulting WCT tool. And after we have that data, we need to extrapolate properties of the sample from that data set and then putting it all together in a succinct report. So far, we have gone through the research into the background information and theory for how this works. And we are ahead of schedule on that. Next is the actual data acquisition and analysis of the data set, which we've given ourselves ample time to do and should be able to do in the time we've allotted. Some potential issues we might run into as we're doing this project is more to do with the actual sample fabrication. We're going to try to fabricate a sample for analysis, but if we're not able to do that, there are data sets available that we're going to work off of. The second potential challenge is tool availability. The sit and consult WCT tool have to schedule your time on that, and the members of the team need to be certified to use the tool.